All righty. Looks like we're mostly back. We got a handful of folks still showing up, but that's okay. This is MAC 1140. Today is the 20th of July, and we're going to pick up where we left off last time. So last time we said pretty much everything we want to say about polynomials. So you now know all the tricks and tools that we would expect a calculus student to have at the ready for factoring polynomials, finding roots, expressing polynomials in various different forms, taking ratios of polynomials, dividing one polynomial by another, writing that as a quotient and a remainder, all of that good stuff. So today we're going to sort of take the next natural step. Once you learn how to, for example, do arithmetic with integers, with whole numbers, you start doing arithmetic with fractions. So you guys have learned how to do algebra with polynomials. The fraction version of a polynomial is what's called a rational function. So today we're going to explore rational functions in their own right. There's going to be some new terminology, lots of fun things to talk about. And if there's time, we might get to talking about some inequalities, because that's our last little step before we get ready for the next test. I think we mentioned this a little bit last time. So we finished this material yesterday. Today, we're going to talk about rational functions, and we may get into polynomial and rational inequalities. This is something that we've actually addressed in the past. It's part of the preliminary material, but we'll be addressing it kind of fresh a little bit today. So, or if not today, tomorrow. That means we need to talk about exam 2, because see, exam 2 comes after section 3.7, which is either what we're going to hit today or tomorrow. I want to set a firm date for exam 2. So let me go ahead and get us into the formal class mode. All right. So, as always, this is MAC 1140. Pre-calc. Today, like we said, is the 20th. Big goals for today.
A little blurry, Professor.
Oh, sorry. Thank you. Focus. There we go. Today, we're going to talk about rational functions, which is section 3.6. And we'll definitely finish that. If there's time, we may get into section 3.7, which is on polynomial and rational inequalities. What we have in the past just referred to as nonlinear inequalities. And the techniques are going to be the same as they are in section 1.8. It's just that we'll be kind of looking specifically with polynomial and rational functions. I'll be able to show you some tricks that work better for those class of functions rather than like all nonlinear inequalities. But first, we got to talk about what rational functions are. So that's going to be the place to start. I do want to adjust one or two things here in my house and change some lights and fans and stuff. So I'll be right back. Okay, here we go. As with all things in mathematics, got to start with the definition. So this is section 3.6. Rational functions. Sort of the most beautiful moments in mathematics come when you make a connection, when you realize that two things that you once thought were totally separate are actually linked together in really important ways. You may remember, as we started talking about polynomials, I said that polynomials form something called a ring. And to a mathematician, specifically an algebraist, someone who studies algebra, a ring is a mathematical structure. It's a collection of objects that obey a certain set of axioms. One of those axioms, for example, is that when you add two polynomials, you get another polynomial. Not everything is like that, right? If you add two functions, you get another function. But if you add a polynomial and like an exponential, you don't get either of those. Rational functions form something even bigger called a field. It has all the properties of a ring. You add two, you get another one. You multiply two, you get another one. But also if you divide two rational functions, you get another rational function. And so in the same way that polynomials are like integers, right? Polynomials are like the function version of whole numbers. Rational functions are like the function version of fractions. And the kind of most interesting or first field that you can discuss is the rational numbers. Turns out rational functions form a field too, which means all sorts of really cool results can be imported from the study of real numbers and rational numbers into the study of rational functions. My wife is calling me. I'm so sorry, guys. Give me 1 second. Hey, baby, what's up? Yes, what's up? Are you okay? All right, I love you. Bye. Oh, she's going to call back. So, definition, that's where we got to start. A rational function is a function of the form, I'll call it r of x, your book uses little r, equals p of x over q of x. And p and q, you remember those guys from the section on dividing polynomials, both represent polynomials, and that's the same thing here. So where p of x and q of x are polynomials. So just like you can take two integers and divide them, the result is called a rational number. If you take two polynomials and divide them, the result is called a rational function. There's lots of things we should say about these, but first I just want to kind of introduce you to the feel of these things, right? And the best way to do that is with a little example. So the prototype rational function, a simple rational function, is r of x equals 1 over x. So here your p of x, your polynomial upstairs, is the constant function 1. It's a degree 0 polynomial. Your q of x is just x. That's a degree 1 polynomial. All right, so this is of the form p over q, where p and q are both polynomials. We don't normally think of 1 as being a polynomial, but it is. It's a degree 0 polynomial. Yeah, thank you, Ainsley. Yeah. The firm date for the exam is Monday. Toss that up here as an announcement. Oh, sorry, exam 2.
I also have a question about exam 3 and the final exam, Professor.
Sure.
I'm actually moving out of my apartment in like 5 days. And then so I have to go home to St. Augustine and then come back and forth for the exams until I move into my new apartment on the 13th. Do you know possibly when the third and final exam are going to be?
The final exam, that date is set in stone.
Okay.
That's the 9th of August. The third exam will be after we finish section 10.4. So I can't say for sure. It depends on how quickly we move through those other topics. But stay in contact with me, and as long as you communicate with me, I'll be able to work with you and figure something out.
Perfect. Thank you.
But yeah, exam 2 next Monday, 7/26. Okay, simple rational function, 1 over x. 1 over x. The polynomial p is the constant polynomial, or the degree 0 polynomial 1, and the downstairs polynomial q of x is the degree 1 polynomial x. So this does fit this definition. Let's take a look at its graph. kind of without thinking too hard, I'll just pick some numbers that I want to plug in as x values and make a little table here. I'll say -3, -2, -1, 0, 1, 2, 3. If I plug -3 into this function, I get -1/3 out, or -0.33 repeating. If I plug -2 in, I get -1/2 out. If I plug -1 in, -1 over 1 is -1. When I plug 0 in, this is undefined. Right? 1 over 0, that's not a number. If you plug +1 in, 1 over 1 is 1. If you plug +2 in, you get 1/2. You plug +3 in, you get 1/3. So what does the graph of this thing look like? 1 over x is a neat kind of prototype. You can kind of think of it as the parent function for a lot of your basic rational functions. I'm going to chop this up here. It's like 1, 2, 3. -1, -2, -3, -1, -2, -. Except when we plug in -3, we're getting -1/3 out. So here's -3 on the x-axis. -1/3 is about 1/3 of the way from 0 to -1. So it's like right about here. -2, -1/2 is the next point on the graph of my function. And then we've got -1, -1. That's going to be like down here. On the other side, right, we're undefined at 0. On the other side, we've got 1, 1, 2, 1/2, and 3, 1/3. This really isn't enough for me to get a full picture of the graph. I have no idea what's going on anywhere like between these guys. You can kind of get a feel for what's happening as we go out here. The graph is sort of settling down. But let's expand our table to look and see what happens when we input, say, -1/2 and +1/2. So what is 1 divided by -1/2? What is this output?
-2.
Very good, -2. And 1 divided by +1/2 is similarly equal to 2. So here I've got -1/2, -2. And over here I've got +1/2, +2. And you can sort of start to see what would happen. If I put in a +1/3, like right here, if I put in this x value, I'd get out a 3. So I'd be way up here. And if I put in a -1/3, I would get -3, which is way down here. So the shape of this graph, you've probably seen this before. I'm trying to bore you or anything like that. In fact, we talked about this as a parent function back in the day. The shape of the graph is like this. And it's got two kind of features that we haven't seen on other graphs so far this semester. As you run further and further off to the right, this graph is getting closer and closer and closer to the line y = 0. And it does the same thing as you run further and further off to the left. Also, as you get closer and closer to x = 0 along the line, along the graph, like as I walk closer and closer to 0 here, my function's going way down. And over here, it's going way up. So this line, x = 0, is special. These dotted lines have important names. This is called a horizontal asymptote. And this guy over here is called a vertical asymptote. And rational functions are neat prototype functions for discovering these things called asymptotes. There is a special notation for asymptotes. They are, in a sense, like end behaviors. So that goes to notation, the arrow notation that we were using before, we'll use that same notation to describe asymptotes. Here, to describe this horizontal asymptote, in the goes to notation, what we notice is that as x goes further and further and further to the right, the y values, they get closer and closer and closer to 0. So we would say as x goes to infinity, y goes to 0. And on the other side, we would say the same sort of thing. As x goes to negative infinity, y is going to 0 there, right? As I wander further and further to the left, this graph is getting closer and closer to this horizontal dashed line, which is the line y equals 0. Things are a little bit more complicated here at the vertical asymptote, because as we approach 0 from the left, we're going down. But as we approach 0 from the right, we're going up. So let me show you that notation. Approaching 0 from the right, imagine you're a little guy walking along this graph. If you're sneaking up on having x value 0 right here, and you're sneaking up from the right, then your x values are positive. So the way we describe that is as x goes to 0 plus. That means from the right. So we'd say as x goes to 0 from the right, my y values are shooting up towards infinity. So we'd say y goes to infinity. And over here, we would say as x goes to 0 from the left, it's a minus above and to the right of the 0, a minus superscript, y goes to negative infinity. So the blue lines there are called asymptotes. A-S-Y-M-P-T-O-T-E, asymptote. And the purple is the goes to notation for describing those asymptotes. I'd like to show you in Desmos kind of what this looks like, so we can kind of zoom around and stuff. I'll add in the lines y equals 0. X equals 0. All right. So you see the blue dotted lines are the asymptotes. And as my, here, the red is the graph of my function. As my x values run off to the right along this graph, the y values are getting closer and closer and closer to 0. And as my x values run off to the left, same thing, my y values get closer and closer and closer to 0. And at the vertical asymptote, as my x values get closer and closer to 0 from the right, the y values, they just blow up, they get huge. This graph gets infinitely tall. So no matter how much you zoom out, this graph gets infinitely tall as you come in from the right, and as you come towards 0 from the left, it blows up, but downwards towards negative infinity. So those are called asymptotes, and asymptotes are a feature of many rational functions. Let me describe to you the sort of notation. That arrow or goes to notation. If you take honors Calc 1, you'll learn the explicit meaning of this notation. But in regular Calc 1, we still just keep it kind of vague. We talk about getting closer and closer. But here's the meaning, right? So if I say x goes to a with a little minus up here, this means x is approaching the number a from the left. If I say x goes to a with a little plus here, this means x is approaching a from the right. Similarly, if I say x goes to plus infinity, this means x is getting bigger and bigger and bigger. I'd say x is running off to the right. And if I say x is going to negative infinity, this means x is running off to the left. So this is the kind of natural language for describing asymptotes. Because we don't ever actually arrive at that asymptote, you may cross it, but the behavior is that you get closer and closer and closer. Then the definition of an asymptote, there's kind of two of them. We would say the function f of x has a horizontal asymptote y equals L if, as x approaches infinity, f of x or y approaches L, or as x approaches negative infinity, f of x approaches L. So to say a function has a horizontal asymptote, like y equals 2, means that one of the following is true. As your x's run off to the right, the y values get closer and closer to that line, y equals L. Or as your x's run off to the left, the y values get closer and closer to that line, y equals L. The definition of vertical asymptote. So horizontal lines are always of the form y equals a constant. Vertical lines are always of the form x equals a constant. So I'll say here x equals a if, as x approaches a from the left, f of x approaches 1 of plus or minus infinity, I don't care. Or as x approaches a from the right, f of x approaches 1 of plus or minus infinity. So a horizontal asymptote is a horizontal line onto which the graph settles as x moves far away from the origin. A vertical asymptote is a number where the graph of the function blows up to either plus infinity, minus infinity, or one on one side, the other on the other side, something like that. Any questions about these definitions? Anybody seeing asymptotes for the first time? Just curious. I saw these for the first time in pre-calc. Personally, my college algebra class didn't talk about this.
I can't remember if I did it in college algebra, but I do remember seeing these. It might have been in my honors high school algebra.
Cool. Yeah, I appreciate the input. It helped me know sort of where to focus our energy in class. So, anybody else? Previous experience with asymptotes? Feelings about asymptotes?
I saw them in college algebra.
Good, very good. Yeah, here at Santa Fe, we're supposed to teach these in college algebra. Sadly, I know that sometimes it doesn't happen because my wife took college algebra here, but I won't get into that. All right. So the simplest sort of rational functions can be understood as transformations of 1 over x. Remember 1 over x, that's one of our parent functions. And transformations of 1 over x are all going to be rational functions because you're just kind of doing simple transformations to this guy. So it's still going to have that same basic form. These are functions, i.e. functions of the form r of x equals ax plus b over cx plus d. Any function that can be written this way is actually a transformation of 1 over x. So some combination of shifts and stretches and stuff like that. These have a special name in complex analysis for those who are interested in complex numbers. These are called Mobius transformations. Don't impress your next math teacher. Refer to these things as Mobius transforms, you'll scare the shit out of them. That Mobius, by the way, this umlaut over the O, is the same guy as the Mobius strip. If you've ever played with one of those, you take a little strip of paper, give it a half twist, then connect the ends. That's a one-sided object, non-orientable 2D manifold. Same guy coined the term Mobius transformation. You can study these as group actions. They're very, very cool. But for us, we're just going to practice these as transformations. So let's sketch the graph of r of x equals, start with 1 over x minus 3. So here a is 0, b is 1, c is 1, and d is negative 3. I hope you see that this really is in this form. Right? If you plug those numbers in to this thing, you get this. What sort of transformations do I need to apply to 1 over x in order to get this thing? Remind you, here's the graph of 1 over x. This shape has a name, by the way, it's called a hyperbola. Here are the asymptotes. Got a few points. Here's 1, 1. Sorry, 1 half, comma 2. And over here it's negative 1, negative 1. So what sort of transformations do I need to apply to this graph, the graph y equals 1 over x, in order to get the graph of this function, 1 over x minus 3? Anybody feeling brave? Just take a stab. It's okay if you're wrong.
To the right 3.
Yeah, exactly, to the right 3. Right? If I swap this x for x minus 3, that gives me this. And we know when we replace the inside of the function with that function, or that, x minus whatever, that's a shift to the right by that many units. So here's the graph of r of x. I'm going to take 1 over x and move everything to the right 3 units. So this vertical asymptote will move. That vertical asymptote, which I'll abbreviate BA, is now right over here. It's the line x equals 3. The point 1, 1, if I shift that to the right 3 units, becomes 4, 1. 1 half, 2 becomes 3.5 or 3.5, 2. And the rest of the graph, it all looks like this. Negative 1, negative 1 gets dragged to the right 3 units. That will become 2, negative 1. You guys see that the graph on the right over here is the same as this graph, just shifted to the right 3 units. Does the horizontal asymptote change when I drag this thing to the right 3 units?
No.
No,
It doesn't, right? Does not change. So my horizontal asymptote stays this line here, y equals 0. You'll notice me drawing the asymptotes in as dotted lines. You guys should do the same. When I ask you to graph these functions on the test, I want you to draw the asymptotes in as horizontal lines. The other thing I want you to do is label them. So here the HA, horizontal asymptote, is still y equals 0. What's the equation of the VA?
x equals
0.
I heard it in there, x equals 3. So the original VA was x equals 0, and I drag everything to the right 3 units. So the vertical line x equals 0 becomes the vertical line x equals 3. But when you shift the horizontal line y equals 0 left or right, that doesn't change. It stays the same. Okay. I'd like to look at one more like this. So this time r of x is going to be a little more complicated. Let's make it 3x plus 5 over x plus 2. So here a is 3, b is 5, c is 1, and d is 2. That's not a big deal. What is a big deal is figuring out how to write this as a transformation of 1 over x. The trick here is going to be to do some long division, right? In 1 over x and 1 over x minus 3, the degree of the top is strictly less than the degree of the bottom, right? This is a constant over a linear thing. Constant over linear. Here I have linear over linear, degree 1 divided by degree 1. That's what's called an improper rational function. So if the degree of the top is not strictly less than the degree of the bottom, we call that an improper rational function, just like an improper fraction where the top is bigger than the bottom. So here, if I want to kind of clean this up, I'm going to long divide. So the thing I'm dividing by is x plus 2, and the thing that's being divided is 3x plus 5. To turn x into 3x, I multiply by 3. And then if I distribute that, I get 3x plus 6. Subtracting these, this is 0. 5 minus 6 is negative 1. So what we learn is that 3x plus 5 over x plus 2 is equal to 3 plus negative 1 over x plus 2. And writing it in this fashion, I can see what the transformations are. So who can tell me what are the transformations to turn 1 over x into this thing?
to the left 2 and up 3.
Good. Those are in there. There's another one.
Reflect over the y-axis.
Good. So first, remember we always do horizontal scalings, then horizontal shifts, then vertical scalings, then vertical shifts. So I don't have any horizontal scalings, but I do have a horizontal shift. And that's to the left 2 units. That's coming from the x plus 2 in here. Next, I have a vertical reflection, the negative 1 up here. This is the same as negative 1 over x plus 2 plus 3. So here's your horizontal shift, vertical reflection, or reflect over the x-axis, and then your vertical shift. So vertical flip over the x-axis, just for clarity, and then we'd shift up 3. So I'm going to take the graph of 1 over x, shift it to the left 2 units, flip it upside down, then bump it up 3 units. here's 1 over x. If I shift to the left 2 units, my vertical asymptote will become the line x equals -2. And this would be the graph with just that horizontal shift. When I flip things over, that branch will come up here and the branch on the right will come down here. And then I bring everything up 3 units. That's going to move my horizontal asymptote from the line y equals 0 to the line y equals 3. And the result looks like this. Not too shabby, right?
Wouldn't it flip the other way because it's flipped?
Oh no, did I forget to do the vertical flip? Oh shit, I did. I'm so sorry. Yeah. Yes, you're 100% correct. Let's draw it as let's do a sequence of graphs here. So we'll start with 1 over x. That mistake I made. I was trying to do too much at once. I apologize. So here's 1 over x. Then we want to go to the left 2 units. So that's going to look like this. So this is 1 over x plus 2. Then we do our flip, vertical reflection. So that's going to look like this. Then we come up 3. So our final graph here. Take this guy and bump him up 3 units. And we will get something like this. So this is the graph of y equals, it was 3x plus 5 over x plus 2. But the way we got there was by thinking of it as -1 over x plus 2 plus 3, which we found through long division. You may start to notice some connections between sort of the algebra shape of this thing and the features of the graph. Like this vertical asymptote is showing up where the bottom is 0 at x equals -2. The horizontal asymptote has a connection between the ratio of lead coefficients, 3 over 1. And the intercepts can be calculated the same way you always calculate intercepts, either by plugging in 0 to get your y-intercept, or by setting the whole function equal to 0 to get your x-intercept. We're going to talk about that in just a second.
I have a question.
Mm-hmm.
For the test, do you want us to put a point, or is it okay if we like draw these 4 steps and show that we know what the steps are? We just don't plug specific.
Yeah, the standard rule is I want at least 3 points. So I'd say, you want to track 1, 1, 1/2, 2, and -1, -1, something like that through this procedure. So when we drag left, this would become -3, -1. 1, 1 would become 1, +1, and 2, right? Yeah. And then 1/2, 1/2 minus 2 is -3/2. When we flip these, those would become -3, +1, and these guys would become, let's say, -1, -1, and -3/2. And then when we bump everything up, we're bumping up by 3, so -3, +1 would become -4. -1, -1 would become -1, +2. and -3/2, -2, then we bump up through and become, this point would be -3/2, positive. So I do want you to plot a few points. You wouldn't be required to draw the full sequence of graphs or all the points on all of the graphs, but on your original and on your transformed graph, I would want at least 3 points. You'll also have to label your asymptotes, so we might as well go ahead and do that here. My transformed vertical asymptote would be the line x equals -2. My transformed horizontal asymptote would be the line y equals 3. So this now would be a graph that gets full credit. And now when you're sketching these on your own for your own purposes, do you always want to track 3 points? No, it's a bit of a hassle. But on the test, I asked you to do that because I want to make sure that you know what you're doing and that you're capable of tracking those points. So I would practice it a little bit, but then, if you're just drawing the picture to get a feel for what's going on, you don't necessarily need to do that. Okay. So asymptotes are interesting. We want to be able to calculate them in general. And what I'm about to show you is a rule for finding asymptotes. To find vertical asymptotes, let me go ahead and say the function we're working with is r of x, and it's of the form p of x over q of x. Vertical asymptotes will come from places where the bottom is 0. With some caveats. You want to make sure that you've canceled any common factors top to bottom that you can. If there are factors top to bottom that cancel, sometimes you won't have a vertical asymptote from that factor downstairs. So simplify your rational function as much as you can, and then do the following. One of those, find the vertical asymptote, set the bottom equal to 0. This is, we would say, in lowest terms. Horizontal asymptotes when you get to calculus, I'll be able to show you kind of where this rule comes from, but it follows a 3-part rule, a 3-case rule. The first case is that the degree of the top is strictly bigger than the degree of the bottom. And if this is true, then there's no horizontal asymptote. The second case I'll ask you to consider is if the degree of the top is strictly less than the degree of the bottom. And in that case, the horizontal asymptote is the line y equals 0. And then the last and most interesting case is if the degrees are equal. And in this case, the horizontal asymptote is the line y equals the ratio of the coefficients. So that's like what we saw in the last guy, 3x plus 5 over x plus 2. Your horizontal asymptote came out to y equals 3, which is 3 over 1. 3x plus 5 over 1x plus 2. The lead coefficient upstairs was 3. The lead coefficient downstairs was 1. So your horizontal asymptote is y equals 3 over 1, or just 3. All right. While we're here, the domain, so it's asymptotes, right? Just this stuff, asymptotes. The domain of any rational function is all real numbers, except those which make the bottom 0. X-intercepts, you find these by setting the whole function equal to 0, which is the same as setting the top equal to 0. So a fraction will be 0 if and only if its top is 0. And y-intercepts, you always find these by plugging in x equals 0. So these features, if you have the intercepts, the domain, and the asymptotes of a rational function, you should be able to draw a pretty good graph. So with that in mind, let's try to graph one of these. Just a second to finish writing this down. All right, here we go.
Can you go back real quick, Professor?
Sure.
Awesome, thank you.
Alrighty then. So let's go ahead and try to sketch a graph. This time we're going to have a more complicated rational function. It's not a transformation of 1 over x. Neighbor lady came by. Sorry, I'm saying neighbor lady came by, brought us some blueberries. Let's sketch the rational function r of x equals 2x squared minus 4x plus 5 over x squared minus 2x plus 1. Certainly, this is a rational function. The top and bottom are both polynomials. We can find asymptotes. Let's start there. Does this function have a horizontal asymptote? If yes, what is it and why? If no, why not?
Yes, and it would be 2.
Very good, yeah. So the degree of the top is 2. It's a quadratic function. The degree of the bottom is 2. It's a quadratic function. So the degree of the top is equal to the degree of the bottom. Which tells us that the HA is the line y equals the ratio of lead coefficients. So the lead coefficient upstairs is 2, and the lead coefficient downstairs is 1. i.e., the line here, the horizontal asymptote is the line y equals 2 over 1, or y equals 2. What about vertical asymptotes? How do we find these?
You put the bottom equal to 0.
Yeah. So I'm going to set the bottom q of x equal to 0. That means 0 is equal to x squared minus 2x plus 1. How do I solve that equation? Zero equals x squared minus 2x plus 1. What do we do here?
Subtract the 1.
So I've got x squared terms and I've got x terms. When I want to find, what am I looking here for? I'm looking for the roots of a polynomial, right?
So you would factor it. So you could do -2. And then what I do is the -2 with a down arrow to 1 to see what can go into both when you multiply. And I got -1 and 2. So it'd be x plus 1 and x minus 2.
Well, so remember, we actually went over a method for this the other day, right? We're looking for two numbers that multiply to this and sum to this. That's the way I would encourage you to think about it. So I need two numbers such that when I multiply them, I get +1, and when I add them, I get -2. So that's -1 and -1. So this is x minus 1 all squared. In other words, your solutions to this equation are just x equals 1. So that's your vertical asymptote. Now, if you do have another way you like to factor things, that's okay. But make sure you're practicing it enough to be really comfy with it. I know that high pressure environment, don't feel stressed. So we've got our asymptotes. Horizontal asymptote is the line y equals 2. Our vertical asymptote is the line x equals 1. Other stuff you might want to figure out are the intercepts, x-intercepts, and y-intercepts. X-intercepts, we said, come from setting the top equal to 0. So that means 0 would be equal to 2x squared minus 4x plus 5. And to factor this, we need the AC method. AC here is 2 times 5 is 10. B is -4. So can I find two numbers that multiply to +10 and add up to -4? I don't think so. Divisors of 10 are like 10, 1, 5, and 2. And none of those will add to -4. In fact, because this is negative, you know that either both need to be negative or one needs to be negative, one needs to be positive. And this is positive, which tells us they both have to be the same sign. So they'd have to both be negative, but two negative numbers that add up to -4 can't possibly multiply to 10. They're too small. So the roots of the top, which are going to correspond to roots of r of x, the x-intercepts here, if they exist, we'll find them using the quadratic formula. It looks like they won't be real numbers. So since they're not real numbers, we're not going to stress about them. We'll just say this real quick. This is 4 plus or minus the square root of 16 minus 4 times 2 times 5. That's 4 times 10 is 40. 16 minus 40 is, let's see, 16 would be 4 to 20, and 20 to 40, -24. All over 2a, so 2 times 2. These are not real numbers. And just like with parabolas, if your x-intercepts are not real numbers, then they don't show up on the graph, right? The graph is just showing real numbers. So we don't have any x-intercepts. No x-intercepts on the graph. Y-intercepts, we always just plug in 0. So here, r of 0 is 5 over 1, or 5. So the y-intercept would be the point 0, 5. So I've got my asymptotes, I've got my intercepts. We can try to draw a graph. I'll mark this as 1. I'll mark this as 1, 2. I don't have any x-intercepts. So I must be approaching this asymptote here up on both sides. If I approached it down on either side, I would necessarily have an x-intercept. My y-intercept is the point 0, 5. I'll just label this here as 0, 5. I'm a little short for space. And over here, I have to approach this guy. So it's a wonky graph, but it's a graph. And if we wanted to make this like good on a test, I'd plug in a few other numbers, figure out what happens at x equals 3, x equals 4. But for us, this is good enough to get an idea of the shape. And let me just show you in Desmos. Here it is. And you see exactly as we said, x equals 1 is your vertical asymptote. It's not a part of the graph. That's why we use the dotted lines. And y equals 2 is your horizontal asymptote. Not a part of the graph, use dotted lines. Not bad. Is our hand-drawn graph perfectly to scale? Is it the most beautiful thing in the world? Not necessarily. Does it communicate all the basic information? Yes, it does.
So how did you get the y-intercept again?
I'm sorry, what was the question?
The y-intercept.
The y-intercept? Sorry. Yeah, plug in x equals 0. So the y-intercept is always the point on the graph where x is equal to 0, because the y-axis is the line x equals 0. Right? Like this is 0, 1, this is 0, 2. All of the points along the y-axis have x coordinate 0. So for any function, when you're looking for the y-intercept, just plug in x equals 0. That's universally true.
And the 5 is from the top, right?
Well, so we're plugging 0 into the whole function. So the top would be 2 times 0 squared minus 4 times 0 plus 5. So the top is 5. And the bottom would be 0 squared minus 2 times 0 plus 1. So it'd be 5 over 1 or 5. Yeah.
Okay, I got it.
All right. So here's a reasonable picture. It's not the most beautiful thing in the world, but again, it works. If I wanted to describe this vertical asymptote in the goes to notation, I would say as x goes to 1 from the right, y goes to plus infinity. And as x goes to 1 from the left, either side, y is going to plus infinity. And if you're ever unsure, like is it up on one side and down on the other, if you're having a hard time figuring that out, just plug some more numbers in, right? You can always make a table. No one on the planet can stop you from making a table of values to get more points on your graph. And if you're having a hard time figuring out what's going on, that can really help. Another thing that can really help is what we said about multiplicities of roots. So the top doesn't factor. But the bottom, remember, factored as x minus 1 quantity squared. So the vertical asymptote here is coming from a multiplicity 2 factor downstairs. If the multiplicity of the factor that gives you your vertical asymptote is even, then you'll go up on both sides or down on both sides. It'll do the same thing. Just like remember how the local behavior in your roots is like a bounce or a cross, depending on whether the multiplicity is even or odd. Doing the same thing on both sides corresponds to an even multiplicity factor downstairs. Doing opposite things up on one side, down on the other, corresponds to an odd multiplicity factor. Okay. So the procedure for graphing a rational function. You want to find those things that we listed, right? Sometimes it's helpful to take a step back and ask sort of, do you have some steps, right? So steps to graph a rational function. First, factor top and bottom. Right? Factor top and bottom. There might be some stuff that cancels. If stuff cancels, make note of that. Second, find any intercepts. We talked about how to do that. X-intercepts come from setting the whole thing equal to 0, which is equivalent to setting the top equal to 0. Y-intercepts come from plugging in x equals 0. Find vertical asymptotes. And this will also tell you the domain. Because remember, vertical asymptotes come from the bottom being 0, and the domain is always all real numbers except those which make the bottom 0. So when you set the bottom equal to 0, that will tell you your vertical asymptotes and your domain. Find your horizontal asymptotes. There's really only ever one horizontal asymptote for functions like this, rational functions, and that follows from the 3-case rule. And that's it, then you sketch the graph. Maybe make a table if you're unsure. Maybe or plot more points if desired. Sometimes just from that information, it's very easy to see what the whole graph is going to look like. Sometimes you might be a little bit insecure about what happens near an asymptote or where exactly the graph is at some particular x value. So if you want to make a table or plot some more points, it never hurts to do that. I'm going to go ahead and follow these steps to graph one more function, and then we're going to be done with this section. So let's sketch the graph of r of x equals 2x squared plus 7x minus 4 divided by x squared plus x minus 2. Very first thing we should do is factor the top and the bottom. We've talked a lot about factoring lately. The bottom here is going to factor as x plus 2 times x minus 1. And the top here is going to factor as 2x minus 1 times x plus 4. Nothing cancels. If anything did cancel, I would make note of that. If you have two factors top to bottom that cancel perfectly, that will create a hole in the graph of your rational function. But here we have no such things. My next step is to find intercepts. So x-intercepts come from the top being 0. So this factor is 0 when x is equal to 1/2. So I have an x-intercept at 1/2, comma 0. The y value at an x-intercept is always 0. And the other factor upstairs, x plus 4, that's equal to 0 when x is negative 4. So that's negative 4, comma 0. Y-intercepts come from plugging in 0 for x. And that's easier to do in the non-factored version because this and this and this and this will all be 0. So you get negative 4 over negative 2. Let me write it like this. R of 0 is equal to negative 4 over negative 2, which is positive 2. So the point there is 0, comma 2. Those are the intercepts. Vertical asymptotes.
asymptotes. Those come from the bottom being 0. So when is the bottom 0? That's why we factored. The bottom is 0 when x is -2 from this factor, and when x is +1 from this factor. So I have two VAs here. X equals -2 and x equals 1. Horizontal asymptote. The degree of the top and degree of the bottom here are the same. They're both degree 2. And just like that very first example, the ratio of lead coefficients is 2/1. So just y equals 2. So now I'll draw my graph. Vertical asymptotes. I've got one of them over here at -2. Got one of them over here at +1. So I'll label this as x equals -2 and this as x equals 1. Horizontal asymptote, just one, and it's up here, it's the line y equals 2. Intercepts. My y-intercept is 0, 2. That's right here. So what you notice is that we actually touch our horizontal asymptote. That's okay. A rational function can touch, cross, whatever, its horizontal asymptote. That's no big deal. X-intercepts are at 1/2, 0. That's right here. Halfway between 0 and 1. And -4, 0. So this is -1, -2, -3, -4. In order to say how to fill in all the curvy bits, I need to know a little bit about what happens near these vertical asymptotes. Now, a few things. I know I have to approach this horizontal asymptote. It's either going to happen from above or from below. And because I've got an x-intercept here, I know it's going to happen from below. And that would actually tell me that I'm going to approach this asymptote on the left going down. But if you're unsure, make a little table. The behavior near the vertical asymptotes. If I take an x value that's like very close to this vertical asymptote, but on the left, like -2.1, that'll give me an idea of whether I'm approaching this guy up here or down here. If I take an x value that's a little bit to the right of that, like -1.9, that'll tell me whether my arrow goes up here or down here. If I take an x value that's very close to +1, like 0.9, that'll tell me what happens over here, whether I'm going down or up. And if I take an x value like 1.1, that'll tell me what's going on over here, either up here like this or down like this. Again, from what we have, you can actually infer. You don't need to do this, but if it helps you feel better, you can. And you don't actually need the full value here. I don't need this number. I just need to know whether we're positive or negative. So play along with me. I'm going to plug -2.1 into this function. I want you to tell me one at a time which factors are positive and which factors are negative. If I plug -2.1 in for x, is this factor, 2x minus 1, positive or negative, and why?
Negative.
Good. If I take something that's real close to -2 and I plug it in here, I get something that's real close to -4. -4-ish minus 1, definitely negative. So here's what I'm going to do. I'm going to draw a little sign diagram. Negative, I don't know, over, I don't know, I don't know. Okay, what about x plus 4? When I plug in -2.1, is this positive or negative?
Positive.
Good, something real close to -2 plus 4 is definitely positive. What about x plus 2? This is the fun one.
Negative.
Good. Negative 2.1 is a little bit more negative than negative 2. Or you take something a little more negative than negative 2, add 2 to it, you're still a little bit negative. Okay, and what about x minus 1?
Negative.
Negative. Okay, so the top overall is negative times positive, which means the top is negative, the bottom is negative times negative. That's positive. Negative over positive is negative. So if I'm a little bit to the left of this vertical asymptote, I'm negative. That means I have to approach this vertical asymptote going down. And that's what we said earlier, but it's kind of, if you're in doubt, this is a good way to check. So I can say for sure that this piece of the graph over here looks like this, because I need to be approaching this horizontal asymptote, and I need to go through this x-intercept. Now, we could check negative 1.9. If I plug this in here, what sort of signs do I get? Or you could use the multiplicity trick. This vertical asymptote is coming from an odd multiplicity factor, right? This is x plus 2 to the 1, which means you're going to change sign. And this way of thinking is very, very useful when we talk about inequalities. But if you're unsure, you could plug in. If you plug negative 1.9 into here, you get something negative, something positive, and something positive. So what do I say? Negative, positive, positive, negative. Okay, yeah, so negative over negative, positive, good. And that tells me that this piece is going to do something like this. Yeah, I know I'm going to cross the x-axis here rather than bouncing off of it, because this is an odd multiplicity factor. The multiplicity game is your friend. And then as we jump over the x equals 1 vertical asymptote, that VA is coming from this odd multiplicity factor. So I went down here negative, that means I'm going to come back here positive. And then I have to approach this. Another way you could have inferred that we have to be positive over here is because there's no x-intercepts over here. If I was going to come back negative like this, then in order to get up to my horizontal asymptote, I would have had to cross the x-axis somewhere. But I don't have any x-intercepts over here. So there's lots of ways to reason your way there. This is a nice sketch of this graph. And you could fill out the sign charts for each of these. Let's go ahead and do it just so we've got practice. Negative 1.9. If I plug that in here, this first factor would be negative. This factor, x plus 4, would definitely be positive. Downstairs, negative 1.9 plus 2, that would be positive. And negative 1.9 minus 1, definitely negative. So this would be negative over negative, which is positive. And you can do the same for the other two, 0.9 and 1.1. I don't want to burn the timeline, but this is a nice graph. And you can get there using tables if you're unsure after you find these things, or, and what I really recommend, is using the information about multiplicities. As you jump over a graph feature coming from an odd multiplicity factor, you will always change sign, whether that's an x-intercept, a root on a polynomial, an x-intercept or a root in a rational function, or a vertical asymptote on a rational function. All of these factors are odd multiplicity. They're all multiplicity 1. So every time I jump over this x-intercept or this vertical asymptote or this x-intercept or this vertical asymptote, every time I will change sign, meaning I'll go from above to below or below to above. So as soon as you know one little piece, you can figure out everything else. I encourage you, if this feels a little bit weird, to rewatch the video. Rewatch the video, check your notes. Remind yourself what the multiplicity thing did for us when we were drawing graphs of polynomials in the previous section. All right, how am I doing on time? Doing okay. Just for fun, let's look at this in Desmos. Couldn't hurt. We had 2x squared plus 7x minus 4 divided by x squared plus x plus, no, sorry, minus 2. Oh, yeah, it's not bad, right? If I add in the asymptotes, well, so x equals -2 and x equals +1. It's just like our picture. So this stuff feels intimidating at first. I remember learning this stuff and being so intimidated the first time I saw it. It was really scary. It seemed like magic. But if you practice it a little bit, I promise it will stop feeling like magic. The most important thing by far is that in the homework set for these problems, you draw the fucking graphs by hand. Do not just guess in the WebAssign thing. I don't want to be cruel and say you get 1 attempt per question or something shitty like that, because that's not good for anyone. But you must draw the graphs by hand. Don't use Desmos at first. You want to check your work, use Desmos, fine. But practice doing exactly what we just did here, where you draw the graph by hand. Go through the steps, find all the things, draw the asymptotes and the intercepts. See if you can figure out just from that what the graph behavior must look like. If you're still struggling, then make a little sign table like this, and that'll tell you what goes on with these arrows. That should be enough to fill in your graph. If you're still having trouble, come to office hours. I'll be happy to help you there.
For the sign graph, do we use the sign graph and not like actually find numbers because we already have the 3 from the intercepts?
More that we're just lazy. We're kind of plugging weird numbers in here, right? Because we're trying to plug in numbers that are very, very close to our asymptotes. So rather than do the gnarly arithmetic, all I really care about is, does this arrow point down or up? Does this arrow point down or up? Well, if the y value here is negative, then this arrow has to point down. If the y value here is positive, then this arrow has to point up. So I don't really care what the number is. I just care whether it's positive or negative. And so it's a combination of laziness and convenience. All right. If the numerator and denominator have a common factor, I alluded to this a second ago, that means there will be a hole in the graph. This is the last thing I need to tell you.
We can't see you anymore, Professor. We just see the screen.
Oh, very weird. You can't see like the dot cam?
I can see the screen. We just can't see you. I don't know if that was.
Oh, okay, okay. I'm sorry. Here, yeah, we'll bring me back. There we go. Common factors between P of X and Q of X. My bandwidth is limited, so I worry sometimes. Here we go. P and Q, common factors top to bottom. Basically, these just mean there's a possibility of a hole. So this is why your first step is to factor. And if anything cancels, you need to make note of it. Easiest way, examples. So if I have the function r of x equals x minus 3 divided by x squared minus 3x, when I factor the top and bottom, I get x minus 3 over x times x minus 3. Remember the top, that x minus 3, that's x minus 3 times 1, right? Anything is itself times 1. So you can cancel these, and you see that this is really just 1 over x. But the original function would have been 0 when you plug 3 into the bottom. So this is true only as long as x minus 3 is not equal to 0, i.e.
x is not equal to 3. What this means is that the graph of my function r of x here looks just like 1 over x, except it's got a hole at x equals 3. And we know what 1 over x looks like. Got this piece down here. It's got a vertical asymptote at x equals 0. It's got a horizontal asymptote y equals 0. Let me mark here 1, 2, 3. We know that the graph here normally looks like this, but where there would normally be a point at x equals 3, I've got this hole from the canceled factor. X minus 3. That's it. Really not any more complicated than that. So if you have a factor that cancels perfectly top to bottom, gonna have a hole. That's all. There is one other little portion of the textbook here having to do with what are called oblique or slant asymptotes. That's not a section that we cover here at Santa Fe, but at a number of universities, for example, UF, they do cover that. So I'll just say in words here really quickly. If the degree of the top is 1 larger than the degree of the bottom, then you may have what's called a slant asymptote, and you find those through long division. I'm not allowed to test you on it here. It's not an official part of the course here, so I'm not going to beat you up on it in lecture. Is there anything else we want to talk about? I think that's it, lads and ladies. I think that is all of section 3.6. So where are we at with time? 2:38. We got about 12 minutes left. So I'm going to go ahead and introduce the next section, and then I will show you the details next time. So the next section here is 3.7. And this is on polynomial and rational inequalities. And I'll say, if you do this homework set right, it's going to be one of the longer homework sets because there's a lot of algebra steps. The basic idea is we want to solve inequalities of the form f of x is greater than 0, f of x is less than 0, maybe greater than or equal to, maybe less than or equal to, where f is either a polynomial or a rational function. The reason I don't want to dive in on this right now, besides the time factor, is that I really want you guys to finish the current homework set before we do this, because the big connection at the end of the current homework set is to do with multiplicities and how that relates to the graph. Let me just draw a picture.
So will homework 6 be uploaded today? Is that due Wednesday too, or is that due Monday?
The next homework set, I'll put it together today, and depending on where most of the class is, I'll either make it available today or tomorrow. It'll be due next Monday.
Got it. Thank
So let's say this is the point -1, 0, and this is the point 2, 0, and this is the graph y equals f of x. The solution to f of x is strictly greater than 0. Here I'm looking for places where my function's graph is above the x-axis. So that would be in here and over here. And that would be the set, the interval notation. It would be from -1 to 2, unioned with 2 to infinity. And if I wanted to solve f of x is less than or equal to 0, that would be all the places where the graph is below the x-axis. So that's everywhere over here and nowhere else. This would be from -infinity up to -1. And I would include the -1 because f of x is equal to 0 there, right? That's an x-intercept. And that's okay because it's less than or equal to. If you think about the graph of this function, just based on the intercepts and the local behavior near the graph, you can infer one possible function f is f of x equals, let's see, I'd have a factor of x plus 1 from the root here, and the local behavior looks like it's multiplicity 1. And then I'd have a factor of x minus 2 over there, and that looks like a parabola if you just zoom in on that little piece. So that's multiplicity 2. So what we're solving is, let's say in part B, is x plus 1 times x minus 2 quantity squared is greater than or equal to 0. And notice that the numbers that are so important for these solutions are the -1 and the 2 from those factors. The way we're going to do this is how we outlined it before, where you're going to like draw a number line, plot a few points, and then test a point from each region. But I'm going to speed you up. Because of what we know about multiplicities now, you won't need to test a point from each region. You'll need to test a point from at most one region. And if you're slick, you can use end behavior and test 0 points. So that's where we're going to go. That's where we're going to go. This would normally be done by like plotting these things on a number line. 1, 2, and we talked about this at the beginning of the semester. We said, okay, that chops the thing up into 3 regions, and you test a point from each region. However, if you know the end behavior of this function, and I do from the graph, but also I could get it from here, the lead term would be 1x cubed. I know that the end behavior is going to be negative over here. And then since this is a multiplicity 1 root, right, we cross the graph, we cross the x-axis there because this factor is a multiplicity 1 factor. I know my function will become positive in here. And then knowing that I'm positive here and that this comes from a multiplicity 2 factor tells me I won't change sign. I'll stay positive. And thus, if you want to know where is f of x positive, oh, well, from -1 to 2 and 2 to infinity. Where is f of x negative? Oh, from -infinity to -1. And that's exactly what we had here. So there are fast ways to do this if, and only if, you remember all the stuff about multiplicities from the section on polynomials. So I want you guys to finish up the homework on polynomials. And I will go ahead and put together your homework on rational functions and polynomial and rational inequalities. If most people finish that polynomial homework today, or if it's already done by the time I finish the homework, I'll release it today. Otherwise, I'll release it tomorrow when we formally talk about this stuff. Right, any questions for me before I let you guys go?
I have a question about where did you get, or how did the exponent 2 on the x minus 2, where did that come from?
So if I look just at the local behavior near this root, I see that it looks like a parabola. Remember, the local behavior near the roots is something that tells us about the multiplicity of the factor from which that root comes. So because this guy really near here kind of looks like the parabola x squared just shifted over, I know that that's a multiplicity 2 factor. If you want to be really pure about it, what you could say is that I know that this is an even multiplicity factor. It might be 4, but the shape here is kind of parabolic rather than really flat like the x to the 4 shape. So it's a safe assumption that this is a multiplicity 2 factor. Does that make sense?
Yeah.
So I would make sure you're really comfy with this idea of how the multiplicity of a factor affects the shape of the graph. That's what's going to make this next section easy or hard. If you're comfy with the multiplicity thing, then that will help you a lot with graphing rational functions, and it will help you a whole lot with this business of inequalities. And so tomorrow we're going to move kind of quickly through this section, and then we will be ready for the second test. Between tomorrow and the second test, we will cover some other material that won't be on the test. The cutoff for the test is section 3.7. And then the test will be next Monday. All righty.
Will you assign a quiz like you did before?
Yep. Yeah, we'll have a quiz this time, just like last time. Any other questions? Alrighty then, guys, I'm going to go ahead and end the meeting. If you do want to talk about something else, you can come see me in office hours or send me a Canvas message. Otherwise, I hope you have a lovely rest of your day, and I'll see you tomorrow.